Very good. So I'd like to start by thanking my collaborators, Survey for funding and this great conference, and the Institute for Rock Magnetism for a fellowship for allowing me to acquire the data that I'm going to show you today. All right, so the magnetic properties of lunar soils arise from nanophase iron particles that are found in amorphous rims and agglutinates and in the glassy parts of the lunar soils. And they are typically very small, much less than 50 nanometers. So the iron nanophase particles are important not just for understanding maturity, because they are a very good predictor of the maturity of a lunar soil, but also for optical reflectance, because it has such a large impact on our understanding of the mineralogy. So in this talk, we're focusing on lunar soils because they're going to form a benchmark measurement for our ICE50 lunar soil simulants that Jeff is making in his lab using dual laser weathering. In addition, I'm showing here on the right-hand side a first-order reversal curve or fork curve. And we're going to use these to help refine our understanding of the distribution of domains and grain sizes in lunar soils. And I hope to convince you that this relatively new method that was not available back in the Apollo era can provide a lot of new information about the lunar soils. Okay, so in this table, so after that brief introduction, this table, we're going to just launch right into it. And this is actually kind of like a benchmark. Are we doing everything right? So we do a bulk magnetic hysteresis measurements. And the hysteresis on the figure on the lower left is a hysteresis curve that is very typical for lunar soils. There is very small hysteresis right in the center, and it saturates at around 1 Tesla or so. And on the right-hand side, this shows how narrow the hysteresis actually is, with very low coercivity. So just to give you a flavor of the soils we're using 3 highland soils, 4 mare soils. The I sub S over FeO, the maturity index, is on the left, followed by the weight percent FeO, and the relative ilmenite, that is the high or low titanium content, on the right-hand side. So let's just walk through this just briefly. We determine the weight percent of nanophase iron by using the saturation magnetization and dividing that by the bulk magnetic saturation magnetization of iron. And these are very typical values for lunar soils, from 0.1% up to 0.6, 0.7. Then we can look at the ratio, use that number and calibrate that to understand a little bit how the amount of iron, ferrous iron, is reduced to nanophase iron due to space weathering, right? The solar wind, micrometeorite impacts, and cosmic rays. And you notice that varies from about 1.5% up to about 11% of the ferrous iron is converted. And finally, we can look at a term, the remnant magnetization versus the saturation magnetization, which gives us an idea of a domain size. And so for the highland soils, you see a smaller number of about 0.02, 0.027, and the mare soils higher than 0.04. And this is an indication that the highland soils tend to be dominated by superparamagnetic spherical nanophase iron particles, whereas in the mare soils, it is more single domain ferromagnets. Okay, so we can apply other methods to investigate the properties of the nanophase iron, and one of them is an alternating field measurement, AC susceptibility. And so this is a particularly good method to look at the superparamagnetic component and to get an idea of the grain size. And so what we're expecting here, and this theory was worked out by Nail in 1949, and here's an expression: tau is related to the exponential of the magnetic anisotropy divided by kT, the thermal energy. And so as we decrease the temperature and apply a small alternating magnetic field at frequencies of 1, 10, and 100 hertz, we see that the susceptibility initially rises. This is the superparamagnetics are able to follow the field. They go through a maximum, and then the moment then has a relaxation time that is longer than the measuring frequency. And so it becomes a viscous particle, a single domain ferromagnet below that temperature. We can, there are the 2 temperature regimes, and so we can use the out-of-phase component, because now we're applying an alternating field. There's a real and an imaginary component, so we use the imaginary component and the peak there, which we call the blocking temperature. And rearranging the Nail equation, and plotting natural log of 1 over the frequency versus 1 over temperature, we can determine the particle size, right? We find the volume and we back out the particle size. And so in this case, for this particular sample, a highland soil of a submature isobesso refio 53, the particle size of about 14 nanometers. And this fits in very nicely with the model. That is, this is in the superparamagnetic regime. The particles themselves, it is this type of measurement weights toward the larger side, although most of the particles in the highland soils are probably much smaller. Okay, if we look at a Mare soil, here's a submature Apollo 17 Mare soil. The first thing you notice is that there's a discontinuity at 57 Kelvin. This is the Néel transition for ilmenite, the paramagnetic to antiferromagnetic state of ilmenite. And that's for a weight percent of about 13% ilmenite. On the right-hand side, we see a similar submature soil, which is low ilmenite, and there is no such Néel transition visible in this particular set of AC susceptibility measurements. We see only the superparamagnetic or single domain. The other thing you'll notice here is that there is no peak maximum in the AC susceptibility, and this is implying, like the other bulk measurements, that this is single domain ferromagnets. They do not relax against an alternating magnetic field. Okay, so the next thing I'd like to talk about are these first order reversal curves. And rather than walking through all of these figures, instead I want to give you the idea that we're showing on the left-hand figure a relatively fat hysteresis curve compared to the lunar soil hysteresis curves, which are extremely narrow. And the idea here is we're going to fill in all of that space with various reversal curves of measuring the hysteresis back to the origin of saturation. And it turns out that this provides a lot of information, even for the very narrow hysteresis of the Apollo soils. Down here, we're just showing that each particular point that we're measuring maps to a contour plot, and we'll go over that next.
3 minutes.
So this is a fork diagram of Apollo, a very mature Mare soil. The left axis is the interaction axis. The horizontal axis is the coercivity axis. And from this contour plot, we can deduce the following things. First of all, that there's a center peak at the origin, effectively, that this is due to the superparamagnetic or single domain ferromagnet particles. We also have the coercivity tail, which is indicative of magnetic anisotropy, not just magnetocrystalline for spheres, but prolate ellipsoids, some other shape anisotropy exists because iron is a soft magnetic material and should not have that high a coercivity on its own. We also have at the vertical axis at the origin that we have the indication for multi-domain particles. And this vertical spread here in the center is indicating nanophase interactions, dipolar interactions between nanophase particles. So there have been hints of this before in the literature, but this is a direct observation of these phenomena in this fork diagram for an Apollo soil. Let's compare a couple of highland soils, an immature on the top, a submature on the bottom. Very similar features, dominated by viscous superparamagnetic states, a little bit of a coercivity tail and a little bit of multi-domain character, but very little interactions. So the implication is that we do have some multi-domain, but really spherical nanophase iron particles in the sort of the classic sense that we think of the nanophase iron formed in lunar soils. In the Mare soils, it's very different. Here's again an immature, submature, and the mature soil. And we have this dispersion along the vertical axis. This is the multi-domain character. We have dispersion along the horizontal axis. This is the coercivity tail, the shape anisotropy, magnetostatics. And notice in this particular case, as the maturity increases, the coercivity tail also increases. So the contours are meant to be at about the same percent. And so the more mature sample has more magnetostatic anisotropy. So our implications is that in the Mare soils, we have more multi-domain iron. We have interparticle interactions. That's the vertical spread from 0 out to 40, 60 millitesla.
30 seconds.
Along the coercivity axis. And let's get to the last slide. And so I hope I've convinced you that these very narrow coercivity hysteresis loops contain actually a lot of information about the nanophase iron particles, and it's worth reinvestigating and opening up these ideas for the Apollo soils. And this helps us to understand what's going on in terms of the magnetic behavior. So we do need to model the Fork diagrams in order to take these qualitative interpretations and make them quantitative. But this also does raise a question: is where is this multi-domain? What part of the fraction of the soil, the size fraction, contains the multi-domain, which is the one that has most of the nanophase iron, and so on? We think that's going to be found in the agglutinates for the multi-domain.